Thank you. Thanks for the post-lunch slot. Hopefully you're all loaded up on insulin, and I'll try and keep you awake. And I've tempted the IT gods by bringing my own laptop, so we're off to a fantastic start. Right, so connecting web apps to HPC, why would you want to do such a terrible, terrible thing? So I'm working on a project funded by Nectar, the Australian Research Cloud, and what they're interested in is understanding how to connect virtual laboratories to supercomputer facilities throughout Australia, both peak and local HPC facilities like we have at the University of Melbourne. So if you're not familiar with the virtual laboratory, this is a Nectar kind of concept. You also have the idea of science gateways, usually but not always a web app or perhaps a virtual desktop environment that's focused on a particular domain of research. So there's a few examples up here, not everything obviously, looking at astronomy, genomics, geophysics, all kinds of things. The idea is that this is an environment that has the tools that scientists need for their particular domain all ready to go, perhaps some reference data sets that they're working with. And it may be about reducing the barriers to entry to use these tools, or it may be simply a necessity to deal with complex applications and pipelines and moving your tools close to where the data is located. So in the case of the virtual laboratories where they are web apps, and I should emphasize not all, so for instance, the characterization virtual laboratory out at Monash is pretty tightly coupled to their HPC system, so that's a bit different. But for those that are a web application, and there are lots of web applications around, there are going to be a lot more science web apps around, they've got same application architecture as any other, where there's a web server, a database, and something that looks a little bit like a compute cluster anyway that's actually doing the computation, the bulk processing on behalf of that front-end application. So for some types of applications where they're not extremely compute intensive, this works perfectly fine, and there are many already on Nectar and elsewhere that work like this. But what we'd like to do is be able to connect those to HPC when it's appropriate to do so. So an example of that is for the genomics virtual laboratory that I'm working with, and they have most of their tools work quite happily in the little cluster they spun up on Nectar. They're single node things, they don't need MPI most of the time. But they do have a few tools that are extremely RAM intensive, and our current cloud resources don't have the CPU to RAM ratio to support those sort of things. But we do have it on our HPC cluster. So the idea is, can you move these jobs off to HPC, stage the data at the same time, do some work, and then bring it back seamlessly? So ideally everyone knows how to use HPC and Bash and all that kind of thing, but perhaps they don't, and this will allow them to use HPC. So, yeah, let's use supercomputers, let's use cloud, let's use them for when they're appropriate in their specific domains, and try not to get into all these big fights. So the problem with achieving this integration is that every HPC system is a little precious snowflake for very good reasons. We have our own schedulers, we have our own hardware, our own software stacks, our own distributions and versions of Linux. Everyone is a little bit different that you talk to, so you're always SSHing in, but once you're there, everything's a little bit different. The authentication is a whole other problem, which I'd love to talk about as well, but I'll leave that for another day. So the dream would be that an application developer that is going in to work with a group of domain scientists can create a web application that talks to a HPC system without having really detailed knowledge of how that HPC system operates, and more importantly, how all of the HPC systems operate that they might want to target. So I might know a little bit about Spartan at the University of Melbourne, but do I really need to know all the details of NCI and Pawsey and the facilities at Monash and everything else? If my users want to run their jobs via the portal on those systems as well, it's a big ask. At the moment, everyone's kind of hand-rolling this, and when they do that, they end up pretty tightly bound to one particular HPC system, which isn't necessarily what we want. So we don't want platform dependencies, ideally, and if we're doing web APIs, we would like a RESTful API, because that's the API language of the web. So I would love to say I've got all the solutions for this, you can go home. That's not the case. I found a few tools that many of you will already be familiar with that can be cobbled together to take some of the sharp edges off this problem and make it a little bit easier to develop these applications, but it's still going to require pretty close collaboration between those who write application-specific domain, web apps, and HPC admins and specialists like myself. So the two things that I want to talk about today, and there's lots of facets to kind of tackling this problem, are APIs that attempt to abstract some of the details of different schedulers and systems. Some of them you'll be familiar with, some maybe not. And containers. Lev's already talked about them a little bit. If you already know about them, I apologize in advance. This will be a bit boring. So the ideal API, starting with that, we would like to have a consistent interface across schedulers, whether using Slurm or some version of PBS. We should be able to say, I want 10 CPUs, please, and it'll know how to interpret that. We'd like to be able to manage files. We'd like to be able to stage files back and forth and be intelligent about that if we can, meaning it'll know how to handle permissions and metadata and handle faults gracefully. It works across system boundaries. So there might be cases where you're hosting your web application within the HPC cluster and everything's fine, but it might be somewhere completely different. It's across several routers and firewalls away, and you've got to join these systems together somehow. And we don't require any changes to the HPC cluster, ideally. Administrators are rightfully conservative about opening up new ports and services. So if we can just use what's already there and talk to it in its own native language, then we should attempt to do so. And I'm talking about web APIs, and so there's going to be JavaScript and that sort of thing. But if someone wants to write a pipelined application that's using Python or something like that, we would like to have that breadth of support, if at all possible. So the first API I want to talk about that I presume pretty much everyone is familiar with is Drama. And the reason I think you're probably familiar with it is because it's been around for a long time. So this is an example using the Python bindings of Drama. So normally it's C and Fortran, but it does have that kind of wide support. We kick off a session, have a little shell script that I'm running that obviously does nothing, but normally it'd go MPI exec or Python do XYZ. We're passing the number of CPUs where we want. In this case, it's not particularly helpful because we're just passing in a native scheduler command in there that's not really extracting things. We've got the wall time, and we kick the job off and wait for it to finish. Importantly, I have to run this within the cluster, so I have to already have been logged in. I have to have my files already staged across. That's the general shape of how you use Drama. So the first problem with Drama is that it attempts to provide universal support to schedulers with a consistent set of features. And what that means in practice is that if a particular scheduler has a feature that isn't shared by all the other schedulers out there, it isn't included in Drama, and you have to drop down to explicitly pass commands in. So that's not ideal. The other problem is that Drama is more or less abandoned. It came out of a standards process in the start of 2002, 3, something like that. The first version of Drama is widely supported by most scheduler vendors. The second version didn't really get any uptake. I think it was supported by one scheduler. Perhaps they're not interested in interoperability. And so any new features and things that have come along since aren't really getting folded into Drama, unfortunately. But it is out there. You can use it. And for many applications, it does just fine. So no longer active support. You have to be able to SSH in and do all the file stuff yourself manually. But that's Drama. So the next one I want to talk about is Saga, which actually came out of a similar standards-based process, but it's a little bit more flexible in how it operates. So again, I've used the Python example here because I like Python. In this case, we're actually kicking off an SSH context, which means I can run this on my local machine. It'll do the SSH connection, talk to the scheduler, and run things on my behalf. Otherwise, things are much the same. I'm running a dumb script. I've set a wall time. I'm kicking things off. I'm waiting for it to run. So if I go, I'm tempting the gods of IT demos, and that Spartan is online and will accept my job, and the hotel Wi-Fi works. Hey, here we go. So, thank you. You may hold your applause to the end. So, this is, to re-emphasize, it's SSH'd in, it's run some commands, talking Slurm in this case, but if I said go talk to a PBS cluster as well, it would know what to do. So it's running that job. I don't know why it's taking so long to echo hello world, but there you go. Yeah, it's on the other side of the country, it's... There we go. Okay, it finished successfully. Who knew? The other useful thing it does is handle the files. So you'll notice it's got the remote file context that have been brought back to me. So this will basically give you a wrapper around rsync and SCP and those sorts of things, push files out to the cluster, bring them back again, and you're all doing this within the same Python script or whatever other binding you're using. So there's also a C binding, I believe. So this is all quite neat. It is fairly expansible. You can put adapters in to talk to different schedulers that may or may not have the same feature set. So Saga's nice. If you have a relatively straightforward set of needs, I highly recommend checking it out, especially if you push to something like drama. It supports PBS and Slurm, which realistically is going to cover 90% of the clusters you want to talk to. It'll do the files, but we're still not really talking about web-based APIs here. So the last one I want to talk about as far as APIs go is called Agave. And this is a project out of TAC, Texas Advanced Computing Center, out of the US. And this underpins Cyverse, DesignSafe, and a bunch of other very large science gateway portals that are suited for biosciences or for infrastructure engineering in the case of DesignSafe. They all are underpinned by this Agave API. It APIs all the things. So we do files, we do execution systems, we also have metadata that's associated with files and execution systems. We have permission levels that allow us to create files or apps or systems and go all the way from this is my system and my account all the way to anyone in the world can access this, and granularity that goes all the way up with that. We can change resources and have history kept of that and versioning, and it's all event-driven, nice microservices, Docker-based sort of thing. So it does everything, which is good and bad. So for the demo for this, again, let's try doing this again. I'm using the Agave command line interface, which is just a dumb wrapper around curl. We can use curl because this is a proper RESTful API. We just hit it with a get or a post, get some JSON back, and we can interact with HPC system, a generic cloud VM, storage systems. It'll talk different HPC scheduler protocols. It'll talk to different storage systems, all via this simple, well, not simple API, but at least a consistent API. So if I go system list, so I've done this curl command. It's hit that particular URL. If I go back up there, this one here, and we've got this JSON payload back. And these are the systems that I've got access to via my API that I can do things with. So this first one here is a generic Nectar VM that I've created. I've told it how to connect to it and where it's located and what it can do. Here's a storage system. This is if we want to do storage on Spartan, which is our HPC system at the University of Melbourne. If you want to run HPC jobs on it, it knows that it's Slurm. You can go and query these URLs and poke around and do stuff. And there's various other ones here. There's public ones that Agave have for testing and so forth out of TAC. So in terms of actually running something, if I go apps list, these are the things I can work with. The idea of Agave is you have systems, so it can be an execution system or a storage system. Then you have apps, and apps can just be, in this case, again, a dumb bit of shell code that kicks off something more complicated. Or it could be a lot more. It could be moving a container to your environment, staging a bunch of data, making sure a bunch of preconditions are met, and then running a job. And there are various states in Agave to keep track of that over and above what your HPC scheduler will do. So these are apps, and let's go and kick off a dumb one. So if I go through my examples here, I can find the one I want. So that little JSON payload there, there's only 2 lines to it. I won't show you what it is. It just gives the ID of the application that we want to run and a name for it. So we kick that off. This time we're going a post into the RESTful API. That app has a system, a target system that it's associated with. Again, we'll cross our fingers that something's going to happen. And things are going. So that job is pending on Spartan. They call it my job for, which is very helpful. I've got this UUID that I can reference it with. And there's all this metadata and kind of hyperlinked API endpoints that I can poke around with and query when this thing is done. So that's Agave via a RESTful API, and I sense you may not be getting the full potential of this at this point. You're obviously not going to be driving it via curl. Probably a more useful thing to look at is something like this. So this is a simple app that the authors of Agave put together. It's done with Angular.js, so a front-end JavaScript kind of framework out of Google, but it doesn't really matter what you use. This is basically just a way of exercising the Agave API. So for instance, if I go to jobs here, hopefully I'll see the one that I just submitted. I believe that's it there, and it's already finished. So what I want to get across with this, you can go and look at the systems and the apps and all the other kind of constructs that Agave has. The important bit, though, is that this app is entirely front-end based. It's a statically hosted web application. So it's some JavaScript, it's some HTML, it's some CSS files. You can have your app entirely contained within those files, and then you can go and host them on Dropbox if you want to. Any kind of static hosting, you don't need any back-end server at all necessarily to write a science application. You can go to your local coffee shop, find some hipster guy and say, hey, do you speak JavaScript? Yes. Come over here and write this application, and they'll be able to do that for you without having to write back-end code. And if you have the system set up already without necessarily talking to the HPC system directly at all, they'll just have those resources available. So that's Agave. Of course, you don't have to do that. You can write quite complex applications that do have backends and this kind of thing, but it's doing a lot of work for you. So Agave, it is a hosted system out of TAC. I think they have 50 or 60 VMs actually running this service, thousands of users, terabytes, if not petabytes of data and jobs and things going through this. It's standards compliant, it does everything. You may not like any of that, which is fair enough. It's a complex beast to get your head around. You're depending on a third party to keep it online, but it is there, and it's a pretty interesting framework, and this is something we're exploring further in the context of the Nectar grant we have to investigate this. So, on to containers, because APIs and containers, it's the full, gamut of buzzwords, right? So, why do we want containers, and what relevance does this have to doing our web applications that talk science? So Bowtie is an assembly program for sequencer data. It is a fairly common application, but like all these applications, we have different versions. If you go and look at these version numbers here, 225, 229, 112, and then NCI, I didn't look at Pawsey. There's no version that's available on all three systems that's the same. So you can go and ask your HPC administrator very nicely to install it for you, but you might have a pipeline that has a dozen different applications, all with their own versions, all glued together. And are you going to go around to every HPC system and ask them very nicely to install every version of every application in the pipeline that you want? You should certainly try, but failing that, containers are an option. So we have this environment where we have Bowtie, we have different versions. Maybe they have the same command line parameters, or maybe they give completely different outputs, and that would be bad. So Docker, I guess, we get asked that occasionally. This is solved, right? You just use Docker, and as Lev alluded to, we can't use Docker because it's bad. You run as root, and nobody likes that. There are HPC facilities, I believe, that do that anyway, so it's kind of up to you, but we do have Singularity now, which is quite a good sort of framework. Who's used Singularity here personally? Show of hands. So that's good. Only you few people will be bored, and I apologise. So just to give a quick overview of Singularity and a taste of what it does, it just gives you a big file, which is an X3-4 file system that you can play around with and do things in. Unlike Docker, which has the kind of layered file system that you have to deal with, so it's simplified. It's flat network and hardware access. So in Docker, ports in the network and so forth have to be explicitly exposed. In Singularity, all of that's flattened except for the volume mounts. So you say, I want this particular location on my host to be exposed in this particular location within my container. Otherwise, it's pretty straightforward down to the level of getting access to the GPU. That works pretty well. In fact, it's getting very well with like a single GPU flag, I think, in Singularity at the moment. So Well, I'm not going to do a demo of that one. I'm going to do the easy way, the slide-based demo. So the first step in using Singularity is to actually create your container. And the kind of baseline way of doing this is to create a blank file system with nothing on it, bootstrap that with your base OS image of choice. So it might be Ubuntu or some other Debian variant or some RHEL or CentOS kind of thing. That gets you a lot of wins just out of nothing, because you might have a bit of scientific software where they assume you're using Ubuntu or something like that, which is completely different to whatever's on your HPC system. If you can give it what it's expecting, you might have saved a lot of time. You can shell into that container, install software, put any files you might need. It'll be persisted in that container, and you're ready to go. The important thing to note, and I think it's something Lev mentioned before, you can't actually create this container on the HPC system itself, which is a bit of a pain. Your options are either to do this on your computer. I have to do it in Vagrant because I'm on a MacBook, or go and pull a cloud, VM, a Nectar, and do this. That's what I tend to do because it's located in the same data center as a HPC system, so it's very quick to move these containers across, even though they can be a few gig. So that's the first way of doing it. The other way is if you have an existing Docker container that already has everything you need. And in the case of bioinformatics, there are many applications where they have well-maintained current versions on Docker Hub that you can go and pull, convert to a Singularity image, and off you go and use them. In this case, the example I'm giving is Digits, which is a deep learning package out of NVIDIA, which has a web interface, something that would otherwise be a bit sticky to get going on an HPC system. In this case, it's just a one-liner to import that from Docker Hub and turn that into a Singularity image that I can run. So running it is much the same as Docker as well. Instead of Docker exec, we've got Singularity exec. We have the bindings here that go from the temp directory on the host to the jobs directory within the container name, and then I'm just kicking off some bash script there to set an environment variable, run Python digits, and that's the extent of it. If you would do this as a HPC job, it would look something like this. The only thing I'm really doing is importing Singularity and then running it. I believe there is now a Slurm plugin for Singularity, which means you can just specify the image as a Slurm variable up the top there with the other ones, and it'll just run in that container from the get-go. So it's not magic, I guess. There's so much buzz around containers that people think they can do everything. My concerns, I guess, is that if you have compiler flags and so forth that depend on particular kernels and architectures, they're not going to be magically taken care of for you. And so perhaps you're losing out on performance there, or maybe the software just doesn't work at all or gives a wrong result, which is probably worse. The other risk I see is that you can get into the situation of creating golden images. You create your Ubuntu image, sit there bashing at it for a while, installing software, end up with something that does exactly what you want. A year passes and you have no idea how you got that thing in the first place. Docker has this nice sort of philosophy of Docker files where you say, set these environment variables, install this bit of software from this location, configure it like this, and then run it. So even if it's not completely reproducible, you at least have a recipe, and so that's a nice thing to do. And you can do the same thing with Singularity, but man, it's tempting to just jump in and start doing things. So you can supercomputer enable your web app. It's still a bit tricky, and you have to know how these systems work. Things like Agave can make it a bit simpler, but it's not quite there yet. Hopefully it makes things easier. So as I mentioned, this project with Nectar, we don't have enough money or time to provide comprehensive solutions, but it's something we're exploring. If you're interested in this space, if you're creating an application like this, or you're supporting users who are doing something like this, please get in touch. We currently have our own personal deployment of Agave, which is the first one outside the US, as far as I'm aware, that we're testing. And so I'd love to hear from anyone who might want to play around with that, or on the issue generally. So that's it from me. Thank you to Nectar, the various VL managers who spoke to me about how they do things, the authors of the tools, and Lev and Dan, our sysadmins at Melbourne Uni on Spartan. Thanks very much.
Video, stuff like that.
Yeah, I think in any case, no matter what you could do, you can just drop down and say, no, forget whatever you think you know about the scheduling system. Here's the exact flag that I want. That's pretty common across all the APIs. So at last ditch, that's available for you. But otherwise, if it's kind of a hand-rolled thing that doesn't apply to PBS generally, you're a little bit stuck. But you can define kind of abstracts and and wrappers and so forth. So at least that's taken out of your hands a little bit. Not as far as I'm aware. I mean, I've asked this question because, no one wants to be dependent on a third party without any money changing hands and service level agreements. The impression I got from them is very much that they've got so many users and dollars of research funding running through this framework now that they have to keep it going. They've got half a dozen people just on DevOps, I think, to keep it alive. So that gives me some confidence that it's going to be there. In terms of if we were to roll a service in Australia or extend Agave beyond what they already offer to everyone, maybe there's some cost associated with that, but so far they seem quite happy to contribute back and work with us, so hopefully not.
Further to that, do you have any feeling whether Agave might provide a suitable framework to use the general purpose science as opposed to something like ownership?
Yeah, I mean, something like Cyverse is pretty much exactly that you go and bring your Docker container that has, what you need, or a Jupyter notebook or something, configured for your environment. And it seems to be the very common pattern that they're doing in Singularity now is it's a bash script, a Singularity image, and Agave glued together, and that creates many permutations of different software that you can play around with. So Cyverse seems to be quite huge. Design Safe is a smaller, kind of more niche one. But they're very much those sort of PaaS platforms, I suppose. Cool, thanks.